Welcome to everyone who is interested in the Brace Summer of HPC projects. My collaborator, Jonas Eschenfelder, studying at the Imperial College London, and me, Carla Nicolin Schoder from the University of Vienna, were the last 2 months part of a project where we investigated the performance, scalability, and visualization of MPAS atmospheres, which models atmospheres globally and within small geographical regions, to generate things like global and regional climate models, or perform numerical weather prediction, or investigate atmospheric chemistry. Compared to the standard weather research and forecasting model, the MPAS mesh is not arranged along longitude and latitudes, but therefore is out of a centroidal Voronoi mesh, which makes it more accurate and flexible in resolution, and also shows good scaling properties on supercomputers. So we ran this MPAS model on the UK national supercomputer Archer 2, and we're going to show you in the next few minutes our results from the performance tests, as well as present you a few examples of our visualization output.
So what you can see here is the result of one of our experiments that we run. This is a regional cutout above the Western Mediterranean. We used a varying mesh size with cell sizes varying between 60 and 3 kilometers. And we simulated 1 to 8 hours at a time. The first interesting thing you can see here is when you look at the runtime on a single node or with 128 cores, the runtime actually increases linearly with model time, and the runtime per simulated hour stays constant at about 16.5 minutes throughout. This is good as it shows that there is no performance loss as you scale up the problem size. Now, when you look at the speed up, which is a measure of how much faster the model runs as we increase the computing power, we see an initially super linear speed up. This we didn't see in any of the global models, and we think is due to a regional cut having to read in lateral boundary conditions at the top of every simulated hour. What is very promising as well is that the runs stay efficient at over 60% after the runtime plateaus. And with all of this, we were able to simulate an hour of simulated time in less than 3 minutes. And this shows good, strong scaling by MPAS. Now on the weak scaling side, so where we didn't have a fixed problem size, but where we increased the problem size with node count, we did 1 node per simulated hour. We see near ideal weak scaling throughout the model from MPAS, and less than 20% efficiency drop at 8 nodes. All of this shows that MPAS doesn't only show good strong scaling, but also a good weak scaling.
After we ran MPAS on H2, we get as output these compressed netcdf data files, which contain the cell, vertex, and add location. But those are very unpracticable for plotting because, for example, when you think about the temperature, it is attached to the cell location, whereas, for example, the wind speed, which can be understood as a gradient between cells, is attached to the edge location. So we converted these locations to longitude and latitudes to get a consistent connection between our physical parameters and the longitude and latitude. And then we wrote a visualization script in Python. And these are a few examples of this visualization script output from the model run, which Jonas showed already. As you can see, for example, here, this is a run on 1,280 cores for 8 hours, starting at 6 p.m. in the evening, showing the temperature color-coded here. And you clearly see that for the mountain regions here, the Alpines and the Pyrenees, there is a higher temperature drop.
MPAS atmosphere with these unstructured Voronoi meshes allows for variable resolutions inside an atmospheric model. It also shows good weak and strong scaling on Archer 2 and stays efficient even at fast runtimes. Visualization of the outputs is very easily done in Python, which is good as NCAS stopped development of its own plotting language. And due to all of this, the variable mesh sizes and the quick runtimes, MPAS would be very well suited for numerical weather forecasting. As for what's the next step for us, we will write a technical report where we give help in compiling and setting up MPAS on Archer 2, as well as recommendations on how to most efficiently run the models. Thank you so much for listening, and thank you especially to Evgeny and Mario for their continued guidance through this project, and thank you to the Summer of HPC program and the EPCC in Edinburgh who hosted us for this very interesting and fun experience.
Yeah, thank you also from my side, not only for these new insights into high performance computing and the possibility to learn new skills on a national supercomputer, but also on a personal level, experiencing how well this collaboration across Europe worked out.